So in this video, we'll be covering Gauss's law as it relates to electrostatics. So this is the formula you need to know. Iota, which represents the electric flux, is equal to the circle integral of the electric field strength dot dA, so E dot dA, which this represents the area of the surface, is equal to the enclosed charge divided by epsilon naught. So let's start off with a warm-up, a simple one that I'm sure all of you recognize. So you have a sphere of charge, okay, of plus Q, surrounded concentrically by a shell, a conductive shell of neutral charge. Okay? So the distance here is A, the distance here is B, and the distance here is C. We're going to find the electric field strength at each interval. So when R, the radius of our Gaussian surface, which is a sphere, because we have concentric sphere, concentric shell, so we have a concentric sphere for our Gaussian surface. So when the radius of that Gaussian surface is less than A, our electric field strength is going to be 0, because the electric field strength inside of a conductor is 0. And so that's going to be the same line of reasoning for when B is less than R is less than A. Less than C, my bad. Same line of reasoning, right? Now, between A and B is a different story. How do we determine that? Well, that's relatively simple. We're going to take the integral of E dot dA, and that's going to evaluate to, in this case, because we're using a shape with we're using a Gaussian surface with a non-changing surface area, it's a constant surface area, then this is going to be equal to E times A is equal to our enclosed charge plus Q divided by epsilon naught. The A represents the area of our Gaussian surface. So that's going to be the surface area of our sphere, so 4 pi r squared. So as a result, we get E times 4 pi r squared is equal to Q over epsilon naught. Divide both sides by 4 pi r squared, and then you get something that looks reminiscent of the electric field strength formula. Because K is equal to 1 over 4 pi epsilon naught, we can just say, well, this is K, Q over r squared. Right? So that would be our electric field strength. So we know that when R is between A and B, we know that E is going to be equal to K, Q over r squared, the radius of our Gaussian surface. Right? Now what about when it's greater than or equal to C? Well, the overall charge is still Q, because this is a neutral. This is a neutral charge for the shell. So the overall charge is still plus Q. Why? Because this neutral charge, the inside surface becomes negative Q, and the outside becomes plus Q. Because the negative charge is attracted to the positive sphere. And so as a result, we get plus Q, negative Q, and plus Q on the outside. So overall, the charge on the outside would be plus Q, so that's our enclosed charge. So R is greater than C. When we do that, that's just going to be E times 4 pi r squared is equal to the enclosed charge plus Q divided by epsilon naught, which again evaluates to E is equal to KQ over r squared. Now, what if the charge on the shell was negative Q? Well, as a result, the inner charge would become negative Q, all of that charge would be, and the outside charge would be 0. So everything would be the same, right? Except, since this is still conductive, this still would be 0 on the inside of the shell. However, since we only care about the enclosed charge, nothing else changes until we reach the outside. Because once we get R is greater than or equal to C, then what happens? Our electric field strength is 0, because the enclosed charge is 0, because of what happens here. Let's do another example, but this time with, say, area density. So we have a slab here. Our Gaussian surface we're going to use is, we want to encapsulate this entire slab. So we're going to use a cylinder. Okay? So that both sides of the slab have charge going perpendicular to it. In this case, like for an example, flux is what we're measuring for the flux is we use a Gaussian surface and we measure how much flux goes through that surface. That's what we're measuring with the flux. In this case, our flux is mostly perpendicular. So, say this has a uniform density sigma, area density sigma, right? So, what we do here is we have EA, okay, that's equal to our enclosed charge, which we don't know, over epsilon naught. Now, how do we determine our enclosed charge? We need to solve for it. Well, we know that sigma is equal to our enclosed charge over our area, because it's the area density. Since it's uniform, this is all we need to know, because it's the same throughout. No matter the area, our density is going to remain the same. No matter the area of our surface, the area density will remain constant. That's what it means to have a uniform density. So as a result, we just solve for Q enclosed. That's going to be equal to sigma A. So that's going to be equal to sigma A over epsilon naught. The A cancels out, and so we're left with E is equal to sigma over epsilon naught. And then you can, I guess, say that would be equal to Q enclosed over epsilon naught A, but that's the same thing as if you just divided this by A. Since we don't know that, but we do know sigma, this is the formula we want to use. A sphere of non-uniform volume density rho of r, okay, so it's related to the radius of our Gaussian surface, is equal to rho naught, make this look more like a rho instead of a p, rho of r is equal to rho naught times cosine pi r. I feel like this is going to lead to a very, very intense screaming internally as I try to solve this, because I just came up with this. Alright, so let's try to find the electric field strength in terms of what we're given here. So, E 4 pi r squared is equal to Q enclosed, blah, blah, blah. We already know that. Well, in this case, rho is equal to this is also equal to dq over dv. Uh-oh. So, let's solve for Q. So we know dq is equal to rho, which the integral from 0 to Q enclosed. dq is equal to the integral from 0 to r, well, actually, let's not put our bounds yet. I guess 0 to v is equal to rho dv. I guess our bounds currently are 0 to v. So this results in Q enclosed, obviously, right? But then this, we need to solve for it in terms of not dv, but r, okay? Because rho gives you p naught, rho naught cosine pi r. So we solve that. That's going to give you, let's erase this, just to get that out of the way. It's going to give you Q enclosed is equal to the integral from 0 to r, right? Because that's what we want the bounds to be, 0 to r. That would be rho naught cosine pi r dv, but dv is also equal to 4 pi r squared dr, because dv over dr would be that. All right, so now we multiply that by that, and now we have it in terms of r. We can take out 4 pi and rho naught, because rho naught is a constant. So we know that Q enclosed is equal to rho naught, 4 rho naught pi, the integral from 0 to r of cosine pi r dr. Take the integral of this, we end up with 1 over pi sine pi r from 0 to r. So that's just going to be r, because sine of 0 is 0. So that's what our Q enclosed is going to be equal to. The pi's cancel out, and so as a result we're left with 4 rho naught sine of pi r. Alright, then we plug that back into our equation, and so as a result we get that E times 4 pi r squared is equal to 4 rho naught sine pi r, wasn't that much internal screaming, it actually wasn't that bad, over epsilon naught. Alright, divide both sides by 4 pi r squared, the 4 cancels out, we're left with rho naught sine of pi r over pi r squared. I guess we could just say that this is the same thing as 4k rho naught sine pi r over r squared. So that's how we would determine that. All right. Now, let's say that the overall charge of this sphere is plus q. So now we need to solve for rho naught. Well, let's say the radius is r, capital R. Well, now we know that when r is equal to big R, right? Little r is equal to big R, so our Gaussian surface is equal to the sphere, right? It's the same exact dimensions as the sphere. Then we know that Q enclosed, which is equal to 4 rho naught sine pi r, but in this case r is equal to big R, and that's equal to Q, right? So we know that rho naught would be equal to Q over 4 sine of pi r. And then we can plug that in here. Right? Let's remove the k because it's kind of a useless thing. So let's leave it in terms of epsilon naught. So then we have E is equal to rho naught, which we know is Q over 4 sine pi r, right? We'll leave it empty for now. Q over 4, so we know that that's going to cancel out, so we'll leave this as a 4. So that 4 cancels out with this 4, right? And so the sine pi r doesn't cancel out because that's a different r. Not bad. Sine pi r. So that's going to give you Q sine pi r over sine pi big R epsilon naught. And then we can do that and we get, well, this would be equal to k q sine pi r over sine pi big R r squared. Boom. And just like that, that's how that, right here, this is how you determine the electric field strength at any point in that, that sphere. All right? Now here would be a funny trick question. What if this were a conductive sphere? Well, then easily, that E is 0 until you reach the outside. But then once you reach the outside, the overall charge is plus Q. So likely, if it were a conductive, it would give you it wouldn't tell you the charge. You'd have to solve it yourself. And so with that, that concludes our Gauss's law video, and hopefully you have gained some knowledge from this.